Hello students, welcome back to our Mechanics of Solid class. In today's class, let me take Unit 3, Transverse Loading on the Beam. In this class, we will be able to calculate shear force, bending moment on the beams. So this will be shear calculation of shear force and bending moment will be required for all your career and for all your professional career, you can say. So without knowing the shear force and the bending moment, you will not be able to design the beam. For the design of beam, you require it. So study carefully what I am going to teach today. And in today's class, let me teach something about the cantilever beam, various types of beam, various loading on the beam, and sign convention for shear force and bending moment, and few problems on calculation of shear force and bending moment for cantilever beam. Okay, let us get into the subject. Yes, in today's class, we will be studying about the transverse loading on the beam. Transverse loading on the beam is nothing but, what does it mean? A beam is a horizontal structural member. A beam is a horizontal structural member. So this is the direction of the beam. So a beam maybe have support too like that. And the loading will be in this direction. So this is the axis of the beam and the loading will be in this direction, in transverse direction. So it is called as a transverse loading on beam. And when you come to the types of the beam, we have got basically two types of beam. One type is based on the type of support, other type is based on the type of the material. And when the material is concerned, we have got concrete beams, steel beams, wooden beams and composite beams. No explanation is required for concrete beam. That is the beams everywhere you see. And steel beam is made up of I section or channel section or T section, and we have got different section for steel. And that also you might have come across so much of steel beams, but you may not have noticed that. And wooden beams also there. In olden old houses we were using the wooden beams. Now the composite beams are consisting of both steel and concrete together, or steel and wooden concrete together, or steel and wooden like that. It will be having composition of different types of material. That is composite beam. And based on the types of the supports, we have got almost the basic 5 types of beam. And first type is the cantilever beam. That is a beam which has got only one support, right? And the beam will be extended on one side. It will be like that. And simply supported beam will be having two supports, simple supports, and over which the beam will be placed. And beam can be lifted at any time. And there will not be any rigid connection between the support and the beam. It can be lifted. And the overhanging beam we have support, and beyond that support the beam will be extended. Beyond the support the beam will be overhanging. It will be coming out of the support. So this is called as overhanging beam. And fixed beam is beam which will have rigid support. The beam will be driven inside the support. Support will hold the beam. So the beam will not be it will not come up, or it will not have any rotation. It will be rigidly fixing. Whereas in case of simple support beam, when you load the beam, it may bend like this, and support it may come out like that. So this possibility is not available with the fixed beam. And the continuous beam, it will be having many support like that, and it will be having more than 2 supports is the continuous beam. Okay, so this is about the type of the beam and types of the loads. And types of the load is concerned, we have got different types of the load. First load is the point load or concentrated load. So it will be concentrated on only one point. Sometimes it may have many point loads also. Need not be having a one point loading, or it may have many points also. Another thing, the uniformly distributed load. So this will be spread all over the beam, and it will be designated as kilonewton per meter. For 1 meter the load may be some amount. So when you want to find out the total load, multiply the load intensity into the length. So it will be having total load. And here in previous case, just add the number of loads, or each load will be described with a unit called as kilonewton or newton or kilogram. And if you just take the load as it is, You need not multiply with the length. Other thing, the last type of the third type of the loading is uniformly varying load, and it is also called as UVL. So uniformly varying load, it will be 0 at one support and it will be reaching maximum at the other support. So it will be in the form of a triangle. Here the loading value of the loading is the area of the load diagram. Area of the load diagram. Here half is what is the area of the triangle? It is half BH. Here half B, breadth is L, height is W. So this is the maximum load here. So W is the height. So half BH will be, this is H and this is B. It will be the area of the loading. So it will be described in kilonewton. So we have these are three types of loading that is being applied in. It is being used in all types of the beam. Now coming to the shear force, this is our concern. Shear force is our concern, and here shear force is nothing but all the sum of all the vertical forces. Say a beam may be like this, and it may be subjected to many loads. It may be subject to load. You are taking one section, and what are all the load acting here on one side? So if the beam is under equilibrium, what are the load on acting on one side will be equal to the load on the other side. Then only it will be in equilibrium. So shear force is nothing but as a sum of all forces on one side of the beam is a shear force. Okay. The bending moment. What is bending moment? Moment is nothing but force into distance. Force into distance is the moment. Here also we will be considering one section and we will take left section or right section, and the number force into distance. Sum of all forces into sum of moments of all forces. We will be having two or three forces. Forces. Take moment of all the forces and add the moment of all the forces, and on any section sum of moment of all the forces is bending moment. And shear force diagram. So a shear force diagram is nothing but a diagram that represents the quantity, the value of shear force. At any section, if you look at the diagram, you will be able to find out what is the shear force on that section. There is a graphical representation or diagrammatic representation of shear force acting on a beam is called a shear force diagram. The same way, the graphical representation of the bending moment acting on a beam is called as bending moment diagram, that shows some of the moment acting on one part of the beam. At any section, the moment, some of the value of the moment at any part of the section, you can know from this diagram. So this is bending moment diagram. Another thing is very important thing, sign convention. Sign convention for shear force. So whether it is positive shear force or negative shear force, how to calculate this is the sign convention. Here for shear force in a cantilever beam, suppose the load pattern is like that. The load is acting downwards on right side and support is acting upward, on upwards on left side. Load pattern is of this nature. Left, right downward, left upward. So if the load is acting in this pattern, it is called as positive shear. If the cantilever beam is like this and the load is applied here, now the load is acting will be downward and support will be acting in upward. So this pattern will have a negative shear force pattern. So this is what about the shear force pattern, a sign convention for the shear force. Now what is the sign convention for the bending moment? So when you apply load, the beam bends like this. So it is simply supported beam. When you apply load, the beam is bending in this way. A concave bending, concave bending. So it is called as positive shear. This is called positive, and it is otherwise called as sagging moment. So either concave bending or sagging moment, if the loading is giving concave bending, the bending moment due to that load will be negative, positive in nature, and it is otherwise called as sagging bending moment. Suppose the beam is bending in this way. For example, the cantilever beam, if it is like this, when you apply load here, it will bend in this way. If it is a cantilever beam like this, when you apply load, it will bend in this way. So this is making a convex bending. So this kind of bending is called as hogging bending or concave bending, convex bending. So this is negative bending moment. When the load makes the beam to bend in convex form, or then it is called as it is hogging bending moment, and the sign convention, or it will be called as a negative bending moment. Okay, an example, always the simply supported beam will have, sagging bending moment, or it will bend in sagging form, so it is positive bending moment will be there in simply supported beam, or sagging moment they will be there in the simply supported beam. In case of negative bending, cantilever beam will be always subjected to convex bending, so negative bending moment will be predominant in cantilever beam. Here also, whether it is the support is on the left side or the right side, it will bend in this form, so that the convex bending will be happening, so it will produce convex bending. Now let us see a simple problem. A cantilever beam subjected to 20 kilonewton at free end, and it is the length of the beam is 3 meter. So what is the total load on the beam? Total load is the number of load. It is only one load here. So the total load is 20 kilonewton. What are all the load coming here should be taken by the support. Support here. So the reaction should be what are all the load. Equal to the what are all the load acting over the beam. So the reaction will be equal to total load, and the total load is 20 kilonewton. Okay. How to draw the bending moment diagram? So this is having right side downwards and left side upwards pattern. So based on this pattern, the shear force will be positive in nature. So draw a line. So I'm equal to the beam span. Project all these points, load points, and beam project all these points. Draw a line equal to the beam span. Here mark the shear force value. Shear force at B is 20 kilonewton. What is the load acting here? 20 kilonewton. Continue up to the next load. Next load is acting here in this direction, upward direction. So it is also 20 kilonewton, but it is acting in opposite direction, so bring it down. So this rectangular box is the shear force diagram for this particular shear cantilever beam. What is the moment here? For all cantilever beam, the moment at the free end is equal to 0. Moment at free end is equal to 0. Okay. For all cantilever beam, the moment at free end is equal to 0. And the moment at the support, so 20 kilonewton force is acting here. So at support, so 20 kilonewton is acting here. At support, this load into this distance is 3. 20 into 3, 60 kilonewton. So 60 kilonewton meter is the bending moment at the support A. So 60 kilonewton meter. So it is making convex bending. So in cantilever beam, negative bending moment will be there. So below the line, draw the baseline, and below the line on here, it is 60 kilonewton. So mark here and connect this. So this is the bending moment diagram for this beam. What do we understand from here? For any section, here say for example, here, so this is 20 kilonewton shear force, and bending moment is this value is the bending moment for this section. That is what we understand here. Next comes another problem, and here the loading is moved to some distance here. So the total span is 3 meter. Load 20 kilonewton is moved from this point to this point. We have got 3 important points: one support point A, and free end B, other load point C. At C, 20 kilonewton is acting. Okay. Now calculate the bending moment and shear force at all the 3 points. At B, at B the load, no loading, right? At B there is no loading. So this is B. At B there is no loading, so this is loading 0. At C, 20 kilonewton is acting. Okay. At A, continue this one at A. What is the load on that side? This is also 20 kilonewton. So drawing the shear force diagram. So here it is 0, and continue here. Here it is 20, and continue up to the next point and bring it down. We are making a positive shear force because in cantilever beam, so the right side downward and left side upward, so it is a positive shear. So we mark it above the line. Now the bending moment. Bending moment calculation. At B the bending moment is 0, and at C, let us find out the bending moment at B, right? At C also, there is no load here, so the bending moment starts. Load starts here. So the distance between the load and this point is 0. So load is acting here. Distance between load 20 kilonewton and points is 0. Point C is 0. So bending moment at C is also 0. Now coming to the load bending moment at this point A. So what is this distance? So this is load value is 20. This span is 2 meter. So 20 into 2, it is 40 kilonewton meter is the bending moment. So this is the diagram, bending moment diagram. So projecting all the things, you'll be having bending moment and shear force diagram. Okay. Now let us see one more problem. A cantilever beam subjected to the multiple point load, and span is 2 meter. Okay, this beam is subjected like 800 Newton here, 500 Newton here, 300 Newton here. So this is 0.5, 0.7 and 0.8. Let us see what are the salient points. Salient point is support A, free end, and load point C, D, and B. So B is another point, load point, C is another load point, D is another load point. Free end is also D. So at this load points and free end and support, we have to calculate the shear force and bending moment. First, what is the shear force at D? Shear force at D is 800. Shear force at C is this 800 plus this 500. This is 1300. Shear force at B, to add all 800, 500 plus 300. Shear force at B 600. And shear force at A, here also 800 plus 500 plus 300 is continued there. So this is shear force at A is, shear force at A is nothing but reaction at A, that is equal to total load, add all total load, that is the shear force here. So here you calculate, mark the point, from here it is 800 and continue up to this point, and here it is 1300, the value, shear force at C 1300, and shear force at D, you mark this value 1600 here also. So this variation is the load here, this variation is the load here. Okay, so this is the shear force diagram. So this will be having step plate section and bending moment calculation. So bending moment inside at support you have to calculate, at free end you have to calculate, at middle point. At free end, for a cantilever beam, at free end the bending moment is always 0. At support C, it is now the other load, the load acting on the other side into distance. 800 into 0.8, 640, that is the load value here. And for this point, 800 is one load and 500 is another load. 800 into this distance plus 500 is this distance you have to add. You should not consider the load acting here because the distance is 0. So for the bending moment here, 800 into this distance, 0.7 plus 0.8 plus in 500 this into 0.7. Calculating, you'll be getting this value as bending moment at point B. That is at the point B. At point C, we have calculated the remains 640. Okay, here it is 0. Now point A, at point A, 800 into the total distance 0.8 plus 0.7, the 3 span 0.8, 0.7, 0.5 plus 500 into this distance 0.5 into 0.57, 0.5 plus 0.7 into 500 plus here it is 300 into this 0.5. Adding all the distances and all the multiplying with the respective forces, you will be getting the bending moment value here. So mark separately like this, you will be having separate straight line. So this is the bending moment diagram. Here you have to calculate it. You should, the load diagram, the first diagram, the load value should be written with the unit and direction should be marked, point name should be marked, beam distances are to be marked. Here in this part, the pattern should be marked, and each variation, point load variation, the value should be marked, and plus sign has to be marked, and shear force diagram is to be written. Here it should be, this bending moment diagram should be written, and value at the changing point should be written, and this point 0 should be made. This is D, C, B, A, and respective bending moment points are to be written. Okay. Now let us see another case, a cantilever beam subjected to uniformly distributed load throughout its span. Or it is given in generic form, the load value is W kilonewton per meter. So we have to calculate the shear force and bending moment at various points, and we have to calculate, we have to draw the shear force and bending moment diagram. For this, will be going under with a different procedure. Take any section XX such that it is X distance from this B, from section B. Okay, the whole span is L. Now, shear force calculation, for shear force calculation, take any section XX such that it is X distance from free end, that we know, free end. Now shear force on XX is given as W into X. So this is W, value of the load intensity is W, this length is X. So this is W into X. Okay. Now the bending moment on XX is nothing but Wx is the load value and this is the distance factor. So this Wx will be acting at the center and this is X, so this will be X by 2. It is acting at the center. So it is X by 2. So this is X by 2. Okay. So multiplying this Wx square by 2 will be the bending moment on this value. Now we have to calculate the bending moment at the end, free end, and bending moment at the support. Okay. At free end, I mean bending moment, shear force in both sections. So at free end at B, the value of X is equal to 0. Substituting X is equal to 0 in shear force equation Wx. So Wx is, I mean, X will become 0. So W shear force will also become 0. W into 0 will be 0. And shear force at A, coming to shear force calculation, shear force at A, the X will be equal to L. So shear force at A is X will be equal to L. So it's substituting in shear force equation, and it will be WL, it is, W into L, it is equal to WL. Okay, so in shear force diagram, at B shear force is 0, at A shear force is WL. So the connecting with a straight line, and this will be the shear force diagram. Since it is left side downward and right side upward, it is having the positive pattern. So it is positive shear force. Shear force signing is positive. Okay. Now this bending moment calculation, let us go to the bending moment calculation. What is the bending moment equation? Wx square by 2 is the bending moment equation. At B, at the free end, X is equal to 0. So substitute 0 to find out bending moment B. It is WL, 0 square by 2, this is 0. So at B, bending moment is 0. At A, X is equal to L. So WL square by 2 is the bending moment at A. So it is WL square by 2, here it is 0. Connect it with a small parabolic line. Here it is parabolic variation, here it is the straight line variation. Why? In this shear force diagram, the equation is of the form y is equal to ax plus b or ax plus c, right? Here it is in this equation, bending moment is of the form y is equal to ax square plus v. So this is parabolic equation, that is the straight line equation. So here the variation is parabolic in nature, here it is straight line in nature. So this is a generic case, and let us solve one problem with the numerical values for this particular case. Here in this problem, we have taken the numerical value. The numerical value is like this. It is with two types of loading. One is with the UDL, other one is with the point load. UDL value is 1.5 kilonewton per meter. The point load is 2 kilonewton, and it is acting at 1.5 meters from the support and 0.5 meters from the free end. The UDL is throughout the beam. Now, to find out the value of shear force and bending moment at this point C, now let us consider a section XX such that it is X distance from B. Okay, X distance from B. Now, shear force on XX will be Wx. On XX, shear force is, consider only this part. Consider only this part, it is Wx. Okay, and shear force on XS is Wx. The value of W is 1.5. X will substitute different value. At X is equal to 0. If you want value at B, then X is equal to 0. So X is equal to 0. Shear force is 0. So at B, the shear force value is 0. At X is equal to 0.5. That is this point. X is equal to 0.5. Substitute the value of X is equal to 0.5. Shear force value is 0.75. So on this, at this point, we have calculated only this load. The load at this point is not considered. So to consider the load at this point also, now take section x1 here, on the somewhere on this side, x1 here, such that it is x distance from the free end. Now both the loads UDL and 0.2 kilonewton are coming into the consideration. So let us write down the generic equation. Shear force or the x1 will be equal to go W into x plus the point load 2 kilonewton. So value of W is 1.5. X you can find out at any section. So plus 2. So this is simplified form is the 1.5x plus 2. This is here for the equation. So when x1 is at C, when x1 is at C, when this section is at C here, when x1 is at C, value of x is equal to 0.5. Value of x is equal to 0.5. Okay. Substituting this value, 1.5 into 5 plus 2, 2.75. So when x1 is at A, when it moves to A here, the value of x1 will become 2. Value of x1 will become 2. So substituting this value, you will be getting 1.5 into 2, 3 plus 2, 5 kilonewton. So we have got these different shear force values. At free end, it is 0. At C, we have got two values, 0.75 and 2.75. Shear force at A is equal to 5 kilonewton. Now let us draw the shear force diagram for this particular case. Shear force diagram is like this. So at B it is 0. At C, lower value is 0.75. The upper value is 2.75. Okay, this is 2.75. 0.75, this the variation is 2. Okay, because the point load is acting here, so we will have sudden variation. From here to here, it is gradually varying, a straight line. From here, a point load is acting as sudden variation. From here to here, another gradually variation. So at A, shear force value is 5. Here at 2.75, here 0. So mark these values, and it is the shear force equation. Now let us move on to the bending moment calculation. Now move on to the bending moment diagram. Drawing the bending moment diagram. To draw the bending moment diagram, first consider same case. Consider xx such that it is x distance from B. X distance xx. Now bending moment on this xx. Load into distance. Load is wx. Distance is it is acting at the middle. It is acting at the middle point. So this is x by 2. So this is x by 2 wx square. This is a general form for bending moment. Okay. When x is equal to 0, that is at B, what is the value of bending moment? Bending moment, when for substituting x is equal to 0, bending moment will also be 0. When x is equal to 0.5, considering x is equal to 0.5, 1.5 into 0.5 square by 2, it is 0.1875. For already told you, to find out the bending moment, ignore the load acting at that point considered, because there is no distance between the point considered and line of action of the load. Since it is the line of action passing through the point, distance is 0, the moment will not come due to that load. So ignore that load. So we will have at free end, value of bending moment is 0. At here you have found out the value of bending moment is 1.875. Okay. Now consider section x1 here away from C on this side. So considering C as the middle point, we are taking one section on this side and one section on the other side. Now write the generic equation. W into x1 is the load and x1 by 2 is the distance. x1 by 2 is the distance. 2 into this distance. So this distance is x1 minus 0.5. x1 minus 0.5. Okay, this distance is x1 minus 0.5. So simplifying w x1 square by 2 and w2 into x1 minus 0.5. Okay. Now to find out bending moment at C, Let us check it once again. Find out, we have already calculated the bending moment at C. Now here also, in this section also, find out bending moment C. At C, put x1 is equal to 0.5. 1.5 into 1.5 square by 2 plus 2 into 0.5 minus 0.5, this will become 0. So this value becomes 0. So we are getting the same answer. So it is okay. Now bending moment at A. To find out the bending moment at A, put x1 is equal to 2. Value of x1 is equal to 2. 1.5 into x1 value is 2. 2 square by 2 plus x1 minus 0.5. 2 is x1 is 2. 2 minus 0.5. And so, calculating this, the value comes around 6 kilonewton meter. So we have found out source 3 bending moment. Bending moment B is equal to 0. Bending moment C is equal to 1.875. Bending moment at A is equal to 6 kilonewton. Keeping all these things in mind, let us draw the bending moment diagram. So, but bending moment at B is equal to 0. At C is equal to 0.1875. At C is equal to 6. So connect these 2 points with a parabolic curve. So this is the bending moment diagram. So we have to, once the bending moment and shear force diagrams are asked, we have to summarize all those things with the 3 C diagram. First the load diagram. Load should have, span and loaded value. The basic load diagram should be there. After that, the shear force diagram. All projection lines should come in a straight line. So the point should come in straight line. So construct the bending moment and shear force diagram as shown. So this is the method to find out the bending moment and shear force. I think you might have understood all those things. So keep all this in mind in try to solve the problem.